FQ14, Laplace transform number 3, we need to solve this LC circuit word problem. Okay? Yeah. So, all right. Use Laplace transform. Yeah. All right. So given, yeah, so the, LC, very simple V function. V function, it's a piecewise function. 1 minus e to the negative t in interval between 0 and pi. Yeah. And outside this interval, t greater than pi is 0. Then, initial condition, 0 initial current and a charge. Initial condition. And we need to find a little q function and I function. Yeah. Actually, we only need to find a little q function or little I. Yeah. Little q, then we take derivative, we get I function. Yeah. All right. In our homework question, you don't need to find little q. Yeah. You only need to find I. Okay. So you can take a derivative directly and find the I. Yeah. All right. So when we start, we get this original equation. Yeah. So with q function, I function. And we know little I is derivative of q, so that little I, we know it's a double q double prime. I prime equals q double prime. Yeah. So let's solve this equation for q function first. Yeah. I just another derivative. We can get it. Okay? Yeah. So let's solve this equation. Q double prime, because capital L is 1. 1 is gone. Okay? Capital C also 1. Division by 1 also gone. Okay? So you get a simplified version. Q double prime plus Q equals V of t. Then let us apply Laplace transform. Both sides. Yeah. All right. The V function, we represent 1 minus e to the negative t. Then, because this interval, we use the U function represent. Yeah. So we use this way a lot. Yeah. Then, the left-hand side, Laplace transform, very simple. Okay? Because 0 initial current and the charge, 0 initial current, we know, yeah, based on this initial condition. Okay? Charge 0, Q of 0 equals 0. Okay? Current initial, because current is Q prime, right? Current initial 0, that's Q prime of 0 equals 0. You see? Yeah? Yeah. That's the reason our Laplace transform here, very simple. S squared plus 1, parenthesis times capital Q, left-hand side, Laplace transform. Yeah, a little hard, we need to calculate the right-hand side, Laplace transform. Yeah, a little harder. Yeah. All right. Let's represent term by term. Term by term. Okay. Yeah. The first, U function, first U function, second U function, 2 terms. But we may need to split another time. Yeah. Yeah. If you can handle this, you do not need to split. Okay? If you still feel hard to handle, then we do another round split. Okay? Yeah. Term by term. For beginners, it's better to do the, all these specific split for beginners. Yeah. But when you have a lot of experience, right, probably you can bypass this step. Okay? So you can apply formula on that directly. Yeah. Yeah. But for beginners, so you may like to split as the simplest forms. Yeah. All right. Now, next we apply formula. Okay? So next I copy the formula. So one formula here is like that. One formula, Laplace transform, the first shifting formula, first shifting formula, and another one. Okay, all right. Then the first term, f is 1, right? A is 0. Yeah, look at that. So we can apply this formula. Little a here, a 0, f is 1. 1 times u. Okay, 1. All right. Here, Laplace transform of 1, that's 1 over s. All right, 1 over s. All right. A0, e to the 0, that's 1. So 1 times 1 over s. That's the first term. Second term. Okay? Still the same function. Okay? All right. But a is 0, right? A is 0. F function is the e to the negative t function. A is 0, okay? So this e is gone. We only need to calculate capital S. Laplace transform of e to the negative t. Okay? E to the negative t, a equals negative 1. Okay? E to the negative t, that means a equals negative 1. So Laplace transform of this function equals 1 over s minus a. A is negative 1. S minus negative 1, s plus 1. Okay? So the Laplace transform of the second term minus 1 over s plus 1. S plus 1. Okay? Yeah. All right. Carefully apply the formula. All right? Try to, connect. Compare the forms. Yeah. Try to connect. So yeah. So you need some practice. All right. Third term. Yeah. Third term, you have a. So here, pi shift a, right? Negative a equals pi. Yeah. F equals 1. So f Laplace transform on 1 over s. Okay. So you get e to the negative pi s over s. Yeah. So e. You have that e. All right. So now this one. Now let me ask you how to work on the last term. Last term, you need to do something. Yeah. How do you work the last term? Any idea? Work on the last term. What formula? So, what direction to go? Can you say something about what direction to go? Recall what we did the first half. First half, we spent a lot of time, right? Sine t squared, we did that. Can you do the similar thing? Sine t and the t squared. Yeah. Because here the shift is different. We want to apply this formula. This formula, you have a shift in f function, same a shift in u function. But here you have pi shift for u function, but you don't have any shift in e function. You need to make that shift. Make up that shift. All right? Yeah. You need to put that shift. Then the offset. Yeah. Plus pi minus pi. Okay? Minus pi plus pi. To get that shift form. Yeah. Here, let me write the formula. Yeah. All right, to write, because look at that formula. Okay. This one, before you apply the formula, let's make that t minus pi parenthesis here, make the same shift, but you need to multiply this e to the negative pi to, offset, make it balanced. Okay? Make it about, yeah. That way, see? So, yeah. Before you apply formula, you need to do this transformation. Okay? After that, this is constant, you can take out, right? Constant you take out, then you can apply this formula. This formula, okay? E to the negative pi s times f. F, you apply for Laplace transform on e to the negative t, that is s plus 1. S plus 1. But here I put this negative pi inside this parenthesis. I have that. All right? Yeah. See? Yeah. So we practice 3 times. The reason we want to apply this theorem, this is our first shifting theorem, not second. Second, that, integral, another one, yeah. First. All right. So we get these 4 terms. That's left-hand side. We have left-hand side, yeah. Left-hand side, yeah. So here, yeah. So this, we have that, okay? So the capital Q can be represented in these 4 fractions. 4 fractions, capital Q. Then we do inverse Laplace transform for each fraction. Inverse Laplace transform, each one. Okay, all right. The first one, let's look at the first one. First one, fortunately, we can find the formula in section 6.9, that big table. So here I just copied formula 19 from that big table. S, omega is 1. Yeah. Oh, yeah. So 1 minus cosine t. That's the first one. We apply the formula. First one. Then, we may need the second one. Now, the first one, all right, so here, the third one, because third one, we apply the same formula as the first one, but we need a shift, right? Look at the shift function. We need to because that one, negative pi s, so we need to shift the function here, this function, the t, shift minus pi, the constant, so no change. The constant, after the shift operation, no change. So you only do the shift operation on the variable t. Apply this formula, so you get third. Then, the second and fourth, you only need to do 1. If you can do the second one, the fourth, you just do pi shift, right? Yeah. Do some shift, okay? Yeah. May not be the pi shift, some shift, okay? All right. Yeah. Here, all right. But here, the second. Let's look at second. Second, easier than fourth one. Yeah. Fourth one, because we need another step. The fourth one. The second, easier. A little easier, yeah. But the second, if you look at all the formulas in section 6.9, 6.8, we couldn't find, it's not easy to find appropriate one for the fraction like that. Yeah. S plus 1. So here you see S plus 1. Here. S plus 1 is a shift, right? So this time shift, you have a shift at the Laplace transform side. Yeah. Or let's say this way. This one, you have a shift at the S side, not T side. Yeah. Our first shifting theorem, the shift occurs at the T side. Okay, T side, not the S side. Then, our second shifting theorem, the shift operation occurs at the S side. So here we need to apply the second shifting theorem. Okay? Yeah. Here. Yeah. But this part is not, in the middle 4. Yeah, because Laplace transform, the middle 4 questions related to Laplace transform. In those 4 questions, I didn't give you I didn't give you questions using the second shift theorem, second shifting theorem. Okay, this one. Yeah. So then it's not required for the final. Okay, so the second shifting theorem, although it's useful, yeah, but for the final, it's not required. Okay, it's not required. All right, but I may like to do this. Yeah. So today I do not do that. Yeah, because today we only have 15 minutes left. I want to do the remaining part. So today I want to, stop this question. Just stop here. But I want to say things like this. Okay. So next week the training session. So if I can find time, I like to show you the second shifting theorem. Calculate this one, and in the final, I may give as extra credit questions. So not the regular questions, okay, for extra credit. So if you can understand my solution, and if you can apply the same method to calculate, then you earn extra credit, okay? Yeah, so not, yeah. I want to give you as optional question. Okay? Yeah. Practice a question similar to this one. Yeah. Similar to this one. Okay? But I show you how to solve, how to apply second shifting theorem to solve it. Yeah, but it's optional. Not required. Okay? Not required. Yeah. All right. So we finish this question. So the last one, last one today. Yeah, the last one today, and the last one for Laplace transform. Yeah. This one. Okay. Yeah. This one, mass spring system. Yeah. So you saw the picture. Yeah. Here I only modify a few numbers. Yeah. So I didn't change much. I just modify a few numbers. Then I talk about the solution. So in the solution, I emphasize the key step. The key step, then you can use to solve your homework question. Yeah, our homework question is easier than this one. This one, the number I select, actually a little harder than the homework questions. Okay, our homework question, actually this one, it's a relatively easy question, yeah, because when I type my solution, only half page, so I can complete solution. The previous there were one question I typed 2 pages solution, Laplace transform, inverse Laplace transform. I typed 2 pages. This one only half page, the solution. So this question actually pretty easy. Yeah, yeah. All right, let's look at the question. Yeah, question. Because the linear system given, okay, linear system given, the k numbers, here I change a little bit, okay, I change slightly, yeah. So our homework questions, the numbers better, easier, better, yeah. Here I make a little harder, yeah, yeah. All right. So then the initial conditions, yeah. Now let's set up equation. We don't need to set up. We just plug in, right? Yeah. So we just plug in. The first equation, second one, after simplification. Here, we need to, after simplification, we get these two. Yeah. And our homework after simplification even simpler than these two. Even simpler than these two. All right. Then we take Laplace transform. Left-hand side, right-hand side. When we take Laplace transform, we need to use initial conditions. Initial conditions, okay? Yeah, that formula. Yeah. Yeah. All right. And the second one, initial condition, the formula. So we get these two equations. Yeah. These two we know they are algebraic equations. No derivatives, we just solve algebraic equations. Yeah. All right. Then the first one, we can write, combine the terms. Second one, combine the terms. Next, we need to solve this algebraic equations. Yeah. So next, how to solve. So this step, our homework algebraic equation, simpler than these two. Okay, simpler, a little simpler than these two. Yeah, but here the method, the way to solve, the same method. Yeah. So let me talk about. So there is a key step. There is a key step. Yeah. But if you couldn't discover that key step, may be hard. Yeah. But that key step is not too hard. Not too hard to to find. Yeah. All right. Next, let me copy these two equations we want to solve. Right? All right. Our home question, why is simpler? Because you have home question, one here, one here, one there, one there, both one. Okay, simpler. Okay, when you see one here, 6, 2. Yeah. 6 equals 3 multiple of 2. Okay. Which way you want to solve? Here, you observe 6 is 3 times 2. Yeah, so here there is a method. You use this first equation to minus 3 times second equation. So you cancel out the constant terms. First equation, because it's 3 times second equation. So you multiply by 3 on second equation, then you do subtraction. Right. All right. So the first equation equals 6. 6 equals 3 times the second equation. Okay? Second equation. Now, after that, you use 6 to connect these two equations. Then you can ignore the 6. Then you can, simplify y part, y1, y2, y1, y2. Here, I make the coefficient part good enough. You can cancel out s squared plus 1. You can cancel out s squared. Our home question you can also cancel out. Okay? Our home question y2 equals some constant times y1, so you will get a simpler equation like that. Then you plug it into the second equation. Yeah. You can find y1 equals that one. Okay? Then you take inverse Laplace transform. Is it much easier? Yeah. Inverse Laplace transform. Now, do you feel confident to find the inverse Laplace transform here? Very confident when you see the form? Jenny, do you feel okay? Right, omega, yeah. So this is omega. Omega square, all right? Square root, this is omega square, okay? All right. And that one, right? So, right, good. Yeah, so let's make this, 2 times, okay? 2 times square plus omega square. All right. Then 2 times root 3 over 2, this time is sine omega, right? Sine omega t. Okay? Yeah? And the constant. Constant, this you can simplify to 6. Okay? Yeah. But our homework question simpler than this one. Our homework, so when you have the things here, simpler than this one. Yeah. That one is not hard. Okay? That one is not hard. Okay. Yeah. So this, now, the last 2 questions related to our homework assignment. Number 3, part B, and also corresponding to the last questions in the final. All right. FQ number 16. Solve ODE by Fourier series. Yeah. let me show you the question. Find a particular solution of the ODE. R function here given by pi over 4, absolute value of cosine of t if t between negative pi and pi. And then we do 2 pi periodic extension. And the absolute value of omega is not even numbers. Yeah, that's the, the question. Now let's look at the solution. Yeah. Here, when you read the question, we only need to find a particular solution. Okay? So you do not need to write a general solution, although that difference is small. Because we can write the general solution of the homogeneous equation easily, right? Yeah. Easily. Okay? We just add that part. Yeah. Yeah. So the most of the work we need to do is on the particular solution. Yeah. So for this question, let us only do that particular solution. Yeah. All right. Yeah. Here we need to use the Fourier series method. Yeah. Here you can see there is a special requirement. Yeah. Even if I do not say using the Fourier series, when you see the 2 pi periodic extension, you should use the Fourier series. Otherwise, you cannot handle that 2 pi periodic property. Yeah. All right. Let's do the Fourier series extension first, since R function is an even function. Yeah, so you can easily see this is an even function. Yeah. So what is the even function? With the property R of negative t equals R of t. That's the even function. Okay? Yeah. Here we have this property. Yeah. All right. And we have the formula. For even function, the Fourier series formula can be simplified. Yeah. So the general formula can be simplified. So what kind of simplification? You can see we only have the terms, cosine terms, constant term, and the cosine terms, but we do not have the sine term. Because sine term, we know, sine function is an odd function. Now, here, R function, even function, if you have the non-zero sine terms, you just break the even function property. Yeah. So that's the reason, in order to keep the even function property, so we have to make all the odd function terms, the coefficients, 0. Yeah. So here, all b coefficients are gone. Yeah. So let's find all these a coefficients. The first one, we need to find a0 by the given formula. Yeah. So you can find the formula in our notes, in the textbook, easily. Yeah. So let's calculate the integral in this way, because we need to remove the absolute value. Here, in order to remove absolute value, we need to divide the original interval into 2 parts. Between 0 and pi over 2, so here, the cosine function, we know, the graph is like this. Like this, okay? Yeah. So 0, pi over 2, pi, but between pi over 2 and the pi, the graph is below the x-axis, yeah, or t-axis. So when you take absolute value, you flip it. Mirror reflection, so you flip the curve to, the part above the t-axis. All right, that's the reason we take a negative sign. Okay, a negative sign. Yeah. So then you calculate integral. It's easy. You get a 1/2. Yeah. 1/4 plus 1/4. Yeah. Yeah. Because this part integral should be negative. Negative 1/4. 1/4 minus 1/4. So 1/2. Yeah. All right. A0. Then a sub n, this formula. Yeah. All right. And this time we need to, in order to remove the absolute value, we use these two subintervals. Yeah. Yeah. Split into these two subintervals. Yeah. Then we can, here we need to apply, remember the product of two trig functions. We apply that formula. Okay? Yeah. So the basic formula. So you can see we get, these two expressions. Then we need to consider an even and odd two cases. Yeah. Yeah. Their properties are different. Yeah. All right. For the odd case, first let's look at the odd case. For odd case, you can see n minus 1, n plus 1, they are all even numbers. And even numbers, you take integral, you get a sine, even number t. Yeah, look at that. Yeah. So then you plug in pi over 2, 0, pi. You can see all the terms are 0. Okay? Yeah. So you can easily see a sub 2k plus 1 equals 0. Yeah. So here I do not write explicitly, yeah, but if you just work on your scratch paper, you can see that easily. Okay? Yeah. Yeah. So here I just, use imagination to get it, or use, brain calculation to get it. Yeah. Then for n equals 2k, now we need to do the calculation here. Okay? Yeah. Still these two expressions, but we need to get sign expression after the integrations. Yeah. All right. Yeah. So for this expression, now we need to plug in k numbers. Yeah. So when k equals 1, 2, 3, and so on. Okay? Yeah. So if you plug in, you do some calculation, you can see you get coefficients like this. The sign changes alternatively. Okay? Yeah. Like that. Yeah. All right. So the R function, at this point, we have the Fourier series expansion for the R function. Next, we are ready to solve the ODE based on this extension. Yeah. All right. So then, the form of the solution. Yeah. Here, together, complete solution, we need to base on the structure here. That summation structure. Yeah. Yeah. And we use the linearity principle. Yeah. Remember these linear ODE. So we are working on these linear ODE. So there is a linearity property. Linearity property. So we can take advantage here. So the solution form as a summation of individual components. Yeah, here we call the components. These y0, y2, y4, corresponding to individual terms in our Fourier series expansion. In that way, we can simplify the structure. Okay? All right. So we only need to consider the structure, and every time we just take one component. Yeah. This component has the form an times cosine of nt. Yeah. Yeah. Find a solution of this form. That's pretty easy. Yeah. So let's do the work. Yeah. All right. Yeah. Yeah. So here, based on the, our Fourier expansion, so we can, based on so for those non-zero terms, yeah, so we use this 2k, yeah, 2k, yeah, yeah, because for all the subscript, all zero, so we just work on the even subscripts. Yeah. Then the first one, yeah, the first one is structure slightly different from all other components. Now, y0 structure slightly different from all other component structures of other components. So we need to work separately. So let y0 equals a constant c. So let's plug into the, original, yeah, or we plug into this form, yeah, because the double root's gone, so omega squared c equals 1/2, so c equals 1 over 2 omega squared. Yeah. So that's the first component. Okay, so y0 component. Yeah. After that, all the remaining components, we just work on a general form. Yeah. All right, so let's assume y2k equals a2k times cosine 2kt plus b2k times sine 2kt. Okay? Yeah. All right. So then let us do the double derivative, double prime. Yeah. You can see this expression easily. Yeah. So then adding, the y prime, double prime plus omega squared y, you compare the left-hand side, right-hand side, so you can find b2k must be 0. Because at the right-hand side, there is no sine 2k t terms. Yeah. So all b coefficients are 0. Yeah. A coefficients non-zero, and you can easily find the expression like this. Yeah. Now you can get back to our final solution expression. Yeah. So this is our final solution expression. Okay? Yeah. Yeah. All right. So this example, so here I show you all the details. It's very similar to our homework assignment question number 7. Yeah. Actually, when you work on our homework question number 7, it is a little easier than the example here, than our sample example here. Yeah. The easier part is its Fourier series expansion is easier than the one we have here. Yeah. Slightly easier than the one we have here. Okay? Yeah. Yeah. All right. Yeah. So hopefully, if you do not know how to solve our homework question number 7, you just study this solution and understand the details, then it should not be very hard to solve our homework question part B, number 7. Yeah. All right, so next, our last question of the homework assignment and also our final. Yeah. All right. FQ number 17. Apply Fourier series to derive an identity. So here it's a small, interesting application of the Fourier series. Yeah. Actually, there is a very useful result. It's called a possible identity. So here we use that possible identity to show one special identity. Yeah. All right, look at the question. Use the Fourier series of f of t equals -1 if t between -pi and 0, +1 if t between 0 and pi. Yeah. Then we do 2 pi periodic extension. Now use that Fourier series expression. We want to show this identity, this given identity. You know, the summation of the reciprocals of consecutive odd integers. Yeah. Reciprocals of consecutive odd integers, yeah, equals pi squared over 8. Yeah. Yeah. You can compare with our homework question. Yeah, similar. All right, yeah. So let's do the Fourier series expansion. Yeah. First, based on the definition of the function, f of t is an odd function. So, you know, the odd function, it has satisfied the property f of t equals negative f of t. Okay, odd function property. Yeah. All right. So then we have a simplified version for Fourier series coefficients formulas for the odd function. Yeah. So that is, we only have the sign terms. All the a coefficients are 0. Yeah. So we only need to calculate b coefficients. So the formula for the b coefficients. Yeah. Yeah. All right. It's pretty straightforward. Yeah. So, then you get this expression. Yeah. So this expression, then you need to calculate it when n is even and odd. Yeah. Because for even, when n is even, it's 0. Yeah. 1 minus 1, 0. When n is odd, you get a 2. Inside the parenthesis, the value is 2. So 2 times 2 is 4. 4 over pi n. Yeah. All right. So then the Fourier series expansion is like this. Yeah. After that, then the last step, we need to apply the possibles identity. Yeah. So we, in class, I explained how to get the possibles identity. So we estimate the error terms, remember? So we use E, we define E, so that's square error, and E star, right? Yeah. So you can look at the notes. Yeah. Otherwise, if you do not know the derivation details, it's fine. You just apply the formula. Yeah. Here, we only need to bring up the possibles identity formula. Yeah. Yeah. It's like this. Yeah. So this is the general version formula. But when we apply it on the current question, you can see all the a coefficients are 0, all gone. Yeah. So you just take summation of all the b coefficients. It equals the integral. The right-hand side integral, the calculation is very easy. So let's do the calculation. Okay? So the left-hand side, yeah, we can, plug in the numbers. We get, 16 over pi squared, parenthesis, summation of the reciprocals of consecutive odd integers. Right-hand side, the integral calculation, very easy, right? Yeah, equals 2. Pi cancel out, just 2. Yeah. 2, then we can do further simplification, 8, but you need to, represent the big parenthesis. So you get a pi squared over 8. That's exactly the identity we want to prove. Okay, yeah. So we're done. Yeah. So we complete the proof. So we're done. Okay, yeah. Now, after you understand this solution, yeah, so you just do it in the same way so you can solve our last homework question. Yeah. Okay, all right. Yeah, so that's it. Yeah. So that's the